All right, so we are into chapter 5 pretty well. Don't forget we have a test tomorrow for those of you taking the live class. For those of you who aren't doing live, hopefully you've already negotiated with me to take a time. I've put this up in Blackboard so that you can see, so sometimes I am a really nice guy. If you clicked on your course here and under, not announcement, I need content. Oh, here it is. It won't. Let me do fancy. Here we go. And if you scroll all the way to the bottom, what does that say on the bottom? I have X proof. I actually posted that, or actually I made it available yesterday morning to give you an opportunity to do it. So I did that because it was a fair amount of work, but the proof is available to you for those of you who did it. And I was a little wordy in my development of the proof. You don't have to do that level of being wordiness, if you will. My idea is that if I can explain it all to you, you can understand what the process is. But the most important thing what I was trying to convey was really how both the equation, the v of x and the I of x, are both heavily dependent upon the receiving end quantities. So we did the v of x equation when we did that in class to show you how it's all based on VR and IR. I wanted to make sure you also see in I of x how that's the case, because hopefully it'll reinforce it again when we look at, excuse me, the v of s, the equations when we go back through, okay? So everything's going to be based on receiving end quantities. So let's see if I can go back to the chapter 5. I don't know how to make that. Huh. I can't stop the web page. How do I stop this web page? Do I remove it? I'm not exactly sure how to remove the, because it doesn't want to let me go around. I can see that fine. Well, let me just go ahead and do another and then insert the file again. Like I said, this is all sort of a trial. Let's see if this works. Okay, so we're going to go back to our discussion, unless you have any questions about how to get I of x. And I think we already put up this example, the 765 kV transmission line. You have the key thing that we have to do, right? Whenever we do any of these problems, you need to make sure you convert to line to neutral voltages anytime you go ahead and actually start these problems, all right? That's really one of the most important things, because if you use line-to-line voltages, your current is going to be different reference-wise than your voltage, and so you're going to get some wonky results, okay? But the key thing is, we get our voltages here, we get our currents, and then you're going to go ahead and solve for these generic equations. Now, in the real world, you never really look at a voltage that's halfway out on a system. You might look at it for a current, only because you're looking at fault currents. But for voltages, you never would actually look out, someplace on the system. So you're always going to be looking at it at the sending end. So what we want to do is we want to modify these equations to get rid of looking at anything sort of midway through the line. But before we do that, we want to discuss the concept of what is a lossless transmission line. So most of the time, our resistance values are going to be small enough that we can not necessarily neglect them, but we don't have to focus on them so much. And if we do that, we have our characteristic impedance. The Z now is purely imaginary, right? It's equal to square root of L over C, and there's no R. So what we can do is we can design a actual transmission line based on its impedances, and we can determine how much power that line is able to deliver exclusively based on the impedances. So you use that as a design engineer to say, okay, I need to move 1,000 megawatts, 500 megawatts, et cetera, and I'm going to use it based on this impedance data. So the first thing we're going to do is we're going to terminate it with our characteristic impedance, that Z sub C, which is the same as our load impedance. And then that allows us to say that our voltage at our receiving end is the same as our IR times ZC. When we do that, we can make our equations no longer have, because if you remember here, this was equal to, this originally was equal to some ZCIR, and this was VR over ZC. Well, because we've terminated it, right, we've actually got exactly the same values. So those are only a function of VR and IR, all right? So now we're going to define this term, which is our source, our surge impedance load, SIL, and that is the actual value of S that we can deliver. So this is S, this is an MVA or VA, and it's going to be determined based on that Z sub C, as well as the voltage that is at the receiving end of the line. Now, here's where this discussion gets to be a little bit interesting. It tells us everywhere along the length of the line, everywhere, your VR is going to be the same. So the voltage is going to be uniform along the line, as well as the current is going to be uniform along the line when you calculate at that Z sub C. Because what that tells me is all the reactive power that's being provided in a line by, because you have a transmission line, if you recall, looks like this, and it has a capacitor here. So all the VARs that this capacitor can provide are being consumed by the VARs in the inductor. So there's no voltage drop, right? So this R is equal to 0. The plus minus voltage drop is 0 here because all the reactive power that the line needs is actually being provided by the capacitor bank. So there's no voltage drop across the line. And since there's no current going through here, right, because you're getting VARs that are being consumed by the VARs here, the current is exactly the same through the line. So the magnitude of the voltage and the current is uniform across the entire length of the line. Yes, sir?
I get the currents all being the same. It's just a series circuit. But
it isn't a series circuit, right? Because don't I have a capacitor here going to ground?
Yeah, but there's no current flowing.
No, there is. There is.
Minuscule amount, right?
It's a small amount, but there still is current flowing through there, and that is enough current to provide reactive power for the line.
I guess I'm lost on why the voltage is the same all throughout the entire length of the line.
So R, let's do this again. So let's just model it as this, okay? Here's our transmission line, right? Mm-hmm. R is equal to 0. This is an XL, and this is an XC.
So it cancels each other out.
It's not that they're canceling each other out. It's these X sub L and X sub C will be different values. But the Q here is the same that's needed by the Q there. That part of the triangle, exactly. So essentially the line, if I look at my line, right, P is equal to 0, so there's no losses, right? I've got Q of the inductor going up here, and Q of the capacitor exactly canceling it out. So the power triangle doesn't look like anything. There's no P and there's no Q. So if there's no real or reactive power lost in the line, how much voltage drop would I get? None. If I have current flow and no voltage drop, then I get no power loss.
We do have resistance losses.
Well, we're treating this as a lossless line, right? We're assuming that it's a lossless line to make the analysis a little easier. So why is that important? Because this tells us this key parameter here. And it kind of goes back to what Dan was mentioning. If I terminate at my characteristic impedance, then everything is perfectly balanced. If the power demanded by the load is greater than that source impedance, then the current is going to be up, right? The current's going to be higher than what it would be under the Z sub C load. That means I have more current going through here, which means I've got I squared X that increases. The voltage hasn't changed, has it? The voltage is about the same as it was before. So the Q is not enough to consume or to provide the VARs that that line consumes. So if my power is greater than what the load would be because of the characteristic impedance, then I don't actually have that case where they will cancel each other out. Yes, sir?
Are you just talking about line losses, or is the power from somewhere else?
This is the load. So this is if the power to the load, so this is P now. If I add a load that's not the characteristic impedance, then I have too much current going through the system, so now I'm consuming more VARs than the capacitor can provide. If that's the opposite, right? If P is lower, okay, so if P is less than the surge impedance loading, what happens to my current? It goes down, doesn't it? It goes down, so that means that this I squared X value drops, which means that Q sub C here is greater than QL. So if P is less than the surge impedance load, then that's the case. If P is greater than the surge impedance load, that's the case. So either the line will consume VARs or it'll generate VARs. That's what happens at night, right? At night, when there's very little power flow through the system because everybody's sleeping and nobody's doing anything crazy, right? You know, nobody here does anything crazy as it is, right? We're all perfect angels. So at night, you end up generating more VARs in your system because the power demand of the line is less than the surge impedance load. During the day, it's the exact opposite. Which one is harder or more challenging, or which one is a concern at all? Maybe that's a better way. Are you concerned at night or during the day or both? All the time. Because at night, if the voltages get too high because you have all this reactive power, you start blowing things up, right? During the day, if the voltages are too low, then customers start complaining, saying they're getting some flicker and all that stuff. So, trick question, yes. So all the time, ISO New England down in Holyoke, they have to spend their entire time constantly monkeying with the outputs of generators and transmission lines to make sure voltages stay within tolerance. And if you look at what we do in Chapter 6, we do what's called a load flow. It's the official title of it. What is the ultimate output of a load flow? The voltage. If the voltages are within tolerance, then that's usually a pretty good sign you're okay. You still have to do some more work, but you're just constantly running load flows to go ahead and determine that. So a transmission line has a lot of stuff that needs to be analyzed or looked at, but there's three key things in terms of operation. Not even talking about faults at all. This is under normal operating conditions. We have thermal limits, voltage limits, and stability limits, and the longer the line, each of those shifts. So when we talk about thermal, we talk about heat, right? I squared R essentially, and there are limits. Do you all remember what this means? Dal? That's a term that if you work in the utilities world, you might see it. It is drastic action limit. So when your line is at the limit, well, which limit is it, right? If it's at the drastic action limit, that means you continue to go beyond this drastic action limit, which I think is 5 minutes of operation, you will mess up the line. You will anneal the conductor. You will actually start to change the metal properties of the conductor that's associated with it. So all these transmission lines know what these limits are at because you can't exceed those. That's a thermal limit. I'm just moving too much current through the line. And remember, it's only I squared R, right? Doesn't matter if you're moving real power or reactive power. The magnitude of the current is determined by both of those, so it's always I squared R. The next one is voltage limit, which basically we have some resistance and some inductance. I did that backwards. Across the line. And as we increase our power demand of the line, right, what happens? The line starts to consume VARs, right? When we consume VARs, we drop voltages across them. And at some point, our voltage limits are exceeded. You can't run one end of a line at, let's say the receiving end has to be at 345 kV. You can't have the sending end at 500 kV, right? It's just not practical. The equipment can't handle that. So if you get too much of a drop across the line, you're out of luck. Most generators can operate at plus or minus 5% of their nominal ratings and still be able to go no problem. You start pushing plus or minus 5%, you have issues. Transformers with load tap changing transformers. Anybody here work on a load tap changer? One person? Do you remember what the range of voltages were? Plus or minus 10%. So you can go plus or minus 10% of the nominal voltage, so that 345 kV, you can go plus or minus 10% without too much of an issue on the transformer. That doesn't mean the rest of the equipment. So you can get up to 380, 390, or as low as 300-ish, you know what I mean? Around that range. But that's about it. You're not getting to 500 kV. It's not going to happen. So generally, the rule of thumb is if you're trying to exceed a plus or minus 10% across a line, that's the voltage stability limit. What is this stability limit that we're talking about here? What's stability? We've talked about it in this class.
Is it you want a constant voltage at your load end?
Say that again?
You want like a constant voltage at your load end?
Well, that's not a stability limit. That's just a design criteria. We're going to try to keep the voltage at the customers fairly stable. It won't be perfect. It's plus or minus 3% usually at the customers, but we'll try to keep it stable. So what is a stability limit?
Would that be the frequency limit?
No, but sort of.
Does it mean you gotta stay within operating parameters and you can't go outside them?
You always have to stay within operating parameters, but say more. What does that mean about operating parameters? Because there's levels of operating parameters. Do you remember N-1 contingency? NERC contingency criteria? What does that say again?
Thought we weren't talking about faults.
We are.
Okay.
We're talking about faults not from the fault current, but from a perspective. Or it doesn't even necessarily need to be a fault. It could be an operator mistake. I opened up that breaker. Oops. You know, that's maybe perceived as a fault. What's that?
There are lots of things that cause confusion.
Exactly. So N-1 is called contingency analysis. N-1 is a NERC mandate that says the absolute worst case piece of equipment removed from your system. I don't care what it is, the absolute worst case. In New England, it's usually the DC line that comes down from Canada, because it's got, you know, any point in time about 10% of the power. If that trips offline, what should the system be?
Still stable.
Still better be stable.
Well, it's got to be able to pick up the slack of the worst component in the system.
Right, so if you're moving 2,000 megawatts through that line, or if you got Main Yankee, or not Main Yankee, Millstone trips offline, any of those things that happen, the system needs to be able to be stable after that fact. That's called N-1 contingency. You lose the worst case piece of equipment, the system still is stable. It's not in a great place, but it's still a stable system. It's not swinging around in frequency and whatever. So if I'm moving 2,000 megawatts through Maine, and all of a sudden that goes away, Maine and New Hampshire aren't connected anymore, so they start swinging, they start oscillating frequencies because you had 2,000 megawatts going through. Now you got a fault or something happening, and you got Maine starting to speed up and New Hampshire starting to slow down, and now they all have to respond and try to reconnect, reclose back in. If you can't, you'll actually swing apart, and then you'll not be stable. That's called transient stability, essentially. Dan, do you have a question?
Didn't Maine separate itself at one point during a blackout? Wasn't it able?
It does it not all the time, but not uncommon. Maine usually stays in pretty tight.
And then, so what happens after that when they try to get all the grid back on Maine? They have to resync it together, don't they? 'Cause
Yeah, you have to resynchronize. But Maine, it would be unlikely because there's multiple lines going into New Hampshire. So it would be unlikely that Maine would separate. It would usually be ISO New England territory. So ISO New England territory would separate from New York, essentially. So there's a few lines that interconnect. There's a DC line that goes under Long Island Sound. So that's one. And then I think there's 3 or 4 AC lines that interconnect into New York. And those would be disconnected. And that's what happened in 2003. New England became an island relative to the rest of the country. That's why in New England, we didn't lose any load, right? You saw pictures of people in New York, Manhattan, walking across the Brooklyn Bridge. Nobody in Boston was walking that day because all the power stayed on. And that was actually a mistake. It should have tripped offline, but something wasn't set correctly, so we got lucky, I guess. So thermal stability is for short lines. Voltage stability is for medium. And transient stability is for long lines. All right, that's why we talked about the DC lines that go in between the East Coast and the West Coast. Those are long, long lines. It would be very difficult to maintain synchronism and stability between the two, so you don't bother. With DC, you're just like, well, whatever happens, that line can be swinging like crazy on one end. We don't have to be singing on this end, and we'll just go ahead and control the power flow through power electronics. So stability, transient stability is not an issue. But it's getting a little bit interesting, and that's why there's a static VAR compensator. I know a number of people in this class have actually been to Chester to see it. That was installed to help improve some of the stability, and that's only about a 90-mile line into Canada, and that increased the line by 200 megawatts, the capacity, even though it's only like a 40 megavar SVC. So.
Can you explain that a little bit? I've been there and I was asking.
So Chester is, I don't know exactly where it's located.
Maybe Lincoln.
Next to Lincoln, so it's what, 45 minutes from here-ish? So Chester has what's called a static VAR compensator. Static means it's not moving, so it's not a motor or a generator. It's a bunch of power electronics that can switch on some capacitors or inductors, and the idea is that they can either inject reactive power, or they can remove it, depending on how the voltage is of the transmission line, and they can do it because it's power electronics very, very quickly. And so the idea is as the system voltage is moving up and down fairly rapidly, the SVC can smooth out some of those oscillations and sort of stop them from progressing through the line. And so all it does is literally just monitor the line. Voltage is changing this way, that way really quickly. Let's prevent that really rapid change and we'll smooth it out. So it's basically like a damper essentially for the electric power system.
That basically adds Q.
It can add or remove Q. Yep.
Q.
Yep.
Just
It just adds or removes reactive power. So, and it was put in, I don't know, 25 years ago, and they keep upgrading it because it's still pretty important.
They do 2 weeks every year.
They what?
They do 2 weeks every year. They do like 2 weeks of maintenance.
Oh, 2 weeks of maintenance. You got to keep the equipment going. Yep.
Now, if it's static, does that mean they're not changing it?
No, static means that it's not a rotating source that
Okay.
provides VAR support. So a rotating system would be one where you have a motor that can either increase or decrease its excitation to either add or remove VARs. That's a rotating excitation, a rotating VAR supporter. And it just can't do it as fast. Static can just, it'll switch on these power electronic devices and it does it rapidly and it makes changes pretty quickly. Those are part of something that's called FACS.
So Paul, that power electronics, what is that, like a big capacitor bank or a battery?
It switches on a capacitor bank, but power electronics are basically IGBTs, right? Do you remember your electronics classes? IGBTs, MOSFETs, SCRs. I don't know exactly what they use for technology, but they're just literally semiconductor devices that act as switches.
Quickly switching things around.
Yep. How quickly can you switch on a MOSFET? Nanoseconds, right? Is that what you learned in 342? Is it nanoseconds? I don't know. Microseconds? Less than a second. Where for switches or breakers, it might take a couple cycles to get through.
I mean, I'm sure it can be faster than this, but just on the amps that I've worked on, the highest, like switch rate is usually around like 500 kilohertz. So I think that's microseconds, right?
500 kilohertz, so the period is 500 kilohertz, so if you want to do time, just invert 1 over 500 kilohertz, which is 1 over 0.5. So what is that, 2 microseconds?
Seconds is the fastest I've seen.
Did I do that right? Math people? So that's how quickly you can switch, which is much faster than you can switch any electromechanical device. So they might have faster things now, I don't know. But the amplifiers you're talking about, they're only dealing in 12 volts DC. These are at, 345 kV divided by square root of 3. So they might just have bigger regions, depletion regions. So I don't know. That's a better question for Nuri. Anybody here in 342 or 343 this semester? You could ask Nuri and ask him the question saying, for power electronics, what would you subscribe or prescribe for? I think it's IGBTs, but I don't know. Or actually, Dwayne teaches a class that he might talk about that as well. No? Okay, so he might actually know that better. I just don't do any power electronics at that level, so I don't know. Anyway, you can look up FACS, which is flexible AC, right? I don't have to say what AC is. Transmission systems. So anything that uses some sort of a power electronic and has some computer brain behind it, it makes it flexible because you can switch things on or off at low levels or high levels, and you can switch it on very quickly, as opposed to the traditional grid, which is things take time. You got to do a lot of analysis, but these Chester can sit there and run all by itself, right? It just monitors the voltage and it just does things. So that's how that works. All right, so here is our current, and then here is our sending in with the voltages just factored out. So, why is this important? As I said, if I have an idea of the surge impedance load, right? If I know what that Z sub C is, when I'm designing a transmission line, I have some control over the Y and the Z. If I can control that, then I can make a determination to say, what can the power be of the system? Or what will the nominal power be before the line starts to consume VARs or starts to supply VARs, so that I can stay within those stability limits to a certain extent. Okay? So you see at 230 kV, my SIL is about 135 megawatts. Roundabout number. Obviously that's going to change based on the Z and the Y, but roundabout. As I move up to what's the highest in main, 345, notice it's only, 1.5 times the voltage, but look at the surge impedance loading. It's gone up by almost a factor of 3.5, right? So just by increasing the voltage by 50%, I've just picked up my SIL to 3.5 times. And then on and on and on. Now, I can use that to make a determination. How much power can I realistically move? Now, this does not talk about contingency analysis, because contingency analysis, it's too difficult to categorize with just a simple table. Contingency analysis, you've got people working on PSSE that spend weeks running thousands and thousands of different cases to figure out these worst case contingencies, and sometimes it's not obvious. The more casework you do, the more obvious it gets, but for the rest of us, it's not obvious. But in terms of at the very base level, if your system can move a certain amount of power, if you have a short line, we talked about thermal, your multiple is, you can get to at least 3 times what the rating of that SIL is. If you're a medium length line, so 50 or so to about 150 miles, you're going to limit that to about 5%. Remember I said 10%, but you want to always be a little tighter, so 5%. You're going to go up to 1.5 times 3 times. And then if you're getting to a longer line, now we're just limiting in terms of stability, and that has very little to do with voltage ratings and SIL, right? That has to do with, hey, I can only move so much power across the line before my system's going to respond slowly based on the length of the line. So in main, right, a 345 kV line, Almost all the lines in Maine are at least, there's no long lines in Maine. They're all 80 to 90 miles or less. You can run it at up to 3 times 430 megawatts. So you can get 1,300 megawatts in just about max for just about any 345 kV line in the state of Maine. So the 2 lines that go into Orrington from New Brunswick, those are limited to 1,300 megawatts for sure. They actually run, I think, at either 1,000 or 1,200 megawatts, and that's because of the static bar compensator. But they're limited again because you've got some, I don't know if it's voltage or probably is voltage there. Going down south, I don't know how much power they use moving into CMP territory. By the way, does anybody know where the 2 lines from Orrington, the 345 kV lines, where they terminate going south? One's in Cooper's Mills, right? Just outside of Windsor, Maine, which is near Augusta. And the other one is Albion, Maine, which is near Waterville, Winslow, China, right? That area. Then they terminate there. The Cooper's Mill one makes sense. The Albion one, I don't exactly know why it terminates there, but yeah, there's not a lot of load. Even in Cooper's Mill there isn't, but they put it out there because nobody wants a big 345 line in the middle of their backyard if there's a lot of consumers there. So that's how we model. That's why we come up with transmission lines. That's how we come up with the sizing criteria. Very base level. All right? Questions? Yes, sir.
So when they're developing these transmission lines, they have step A, B, C that they're going through. They gotta know the length, they gotta know the load, and they gotta know what they're gonna put in protection devices.
So the question is, when they're putting in a new line, what is the decision making? So it's a lot more arduous process than that. Usually they're doing system planning, figuring out what the load is going to be and where, and they're projecting out, I don't know if it's 5 or 10 years, probably at least 5. There's an ISO New England map that shows some of the planning that they're doing. So they have to make a determination saying, okay, we have way more capacity going in this area than what we can currently support, so we have to figure out how to get that power in there. And then it's up to the individual transmission line operators to figure out how to support that. So a transmission owner would be CMP, Emera. They own the transmission lines in their territory. ISO New England's doing all the load projections and a little bit of backup with the utilities and saying, we need to figure out how to get more power here. So then it becomes a team effort in New England because downtown Boston, you're not going to put 2,000 megawatts of generation. I mean, the land there is just so outrageously expensive. You can forget, nobody's going to bother even putting anything close to Boston. So now you got to start moving out. And so then if you start getting in other people's territory, well, those people have to have generation there. And as long as the price per dollars per megawatt hour, which is the LMP, that becomes something saying, yeah, I think I can actually, I'm willing to pursue that additional cost. So they'll put generation, but you still have to move the power from where the generation is to the load. And at that point, you have to go and put a Public Utility Commission request. I want to go ahead and get authorization to be able to spend money to do this, which is $1 billion+. Then you got to go out and get that approved. And then you got to go and get land, right? You got to get easements, which takes years for people to sign off on. And sometimes you got to go to court via eminent domain to force people to let you access their land. So there's just a whole process. So the actual installation of a new line, it might take 10 years from the time you think you need one to the time you actually get one put in. So that's why you have to plan that far out. Now that's different if you have current right away. Why do you think that they ran another 345 line down south? They tried to follow the existing right away as much as they can because it's easier, right? I already own this right away, or I have access to this right away, so I can do it. Does anybody remember probably 4 or 5 years ago what Governor LePage was mentioning? Run power lines in the I-95 corridor. So run it right underground or overhead. I don't know what he was proposing. The state of Maine owns all this land. It's easy to get easements from the state of Maine. They just say yay or nay, and it's one blanket thing. So then you just put a transmission structure or underground lines right inside the roadway, which the state owns, and then you can't have landowners complaining about because it's just a blanket approval. So Putting it in public access roads is another option, but that's not always the best. Usually it's the best because where do you think most of the people live near? Off ramps for the 95, right? At least in Maine, I don't know about in other states, but so you put most of the load there, that would make sense to have most of the power there, but you still have to have generation, which you're not going to have close to the off ramps because nobody wants to pay, big dollars for property when, you can put a generation 10 miles further out, get much cheaper land and nobody cares.
So the design process is a lengthy process.
Very lengthy process.
To go through, and those are just on the paperwork end. It's not even.
That's just getting it approved. Once you have that approval to build a line, you have a sense of how much land you need. You also, at least in Maine, you're pretty stuck in terms of voltages, right? For transmission, 345 or 138, maybe even 115 kV. So that's pretty much what you have to decide. How much power you're going to use is, all right, we need to move 2,000 megawatts, we're going to 345 kV. We need to move 500 megawatts, we could probably do that at 115 kV. So that's part of the next process, which is what voltage class that they use, and they try to usually go as high a voltage as possible because it gives them more flexibility, but sometimes they can't do that. Costs a lot more money to go 345, but not triple the money as you would think. It's not nearly that expensive, so that's why going a higher voltage is better.
On the flip side of repairing a grid that went down, like say the Bahamas.
Yep.
So they were all wiped out. So they got to rebuild their system. Are they going to rebuild? Is it wise for them to rebuild the existing system, or should they? Right now they got to rebuild something. So should they plan for the future and be upgrading? And then if they got to do that, that's a lot more work for them to do than just build the existing system that's there.
So the question is, if they, like in Bahamas where their electrical infrastructure was damaged or destroyed entirely, they have to rebuild it, what should they be doing? Keep in mind that when you're talking about different countries, they might have a very different approach, which is we can't afford to put fancy systems in. So we need to probably put whatever we need to get, the tourists back to our island. And, if it's Band-Aids and duct tape, they'll do it. And that's not a put down on them. It's just like we don't have the resources necessarily to do that stuff. If that happens someplace on the mainland, they probably would have a little bit of projection into the future, but for the most part, you're just trying to get customers up and online as quickly as possible. So you don't have time to build a system that's going to be good for 10 years because you got people, potentially dying because they don't have power for. They'll probably rebuild what they have. Maybe they'll use a little bit beefier poles, try to go with some different routes if possible. But for the most part, you'll see, 10,000 bucket trucks moving down there, and if the pole's not broken, they'll just restring a conductor over it just to get customers on as quickly as possible.
They can reuse the lines that are laying around and stuff.
Maybe, it depends. Maybe they can reuse it, sometimes they can't. It's usually cheaper if they just start new. Because if a line's laying on the ground, you still have to get it up and string it, right? So if the line is 10 miles down on the ground, they're like, you know what, let's just leave that one de-energized on the ground, and let's just run a new line because they can get wire. I mean, they've got a lot of this stuff in stock, and so it's much easier if it's on a cable reel to pull it. There's a pulley system to do it. It's much easier. All right, so now we understand transmission lines. Now let's build a model that is practical and actually works for us. So that transmission line is just going to be a box. We're just going to treat it as a box. And we're going to use a concept of a two-port network or two-port parameter, which means I don't care what's in the box. I have a port here and a port here. So I have a receiving end and a sending end, both voltage and current, and whatever's inside the box, I don't care as long as the voltages and currents on both ends are the same, right? It's equivalency, essentially. And in this class, we love working with matrices, so let's keep working with matrices. We're going to use our matrix format to solve for Vs and Is, because I have two equations and two unknowns, right? So let's just go ahead and put those in a matrix and solve for those. So this is going to be called our ABCD parameter, because inside our matrix is A, B, C, and D. All right? Now, what we need to do is I have a Vs equation. Whoops, let's go back. Here's a IS equation, right? So we solved for IX or IS, and we also solved for VS. We need to convert these two equations to ABCD, if I can get there. Excuse me. I hope that doesn't blow my mic up. There's our VSIS matrix, our ABCD, and our VRIR matrix. And if we just rewrite those equations, right, we can see that A is that, B is this and this, right? So ZT, C times that. C, oops, got ahead of myself. Didn't mean to fill that in. Try that again. So this is A, B, C, and D, right? Minus the IR. No, we don't ignore IR because remember, VR and IR are multiplying those parameters, so we have to factor those out. Those are the known variables, so we just have to do the coefficients that multiply it. So let's stuff that into our matrix, our ABCD. This is only for what's called our T equivalent, because the letter T looks like that. Let me switch to red because the green may not be legible. That's the T. Do you remember what our model was? We had a capacitor here, a resistor, and an inductor. Doesn't that kind of, sort of look like the letter T? Kind of? Kind of? I know it's a stretch, but I didn't coin it the T. Somebody else did. So this is the T equivalent model, ABCD parameters. All right? That's the T equivalent. Well, that's all well and good, but the world actually prefers a pi equivalent. Does this look like a piece of pie? No, but it looks like the Greek letter pi, sort of, right? So this is the pi equivalent model, and the pi equivalent model has to have exactly the same results as the T equivalent, right? For those to be equivalent circuits. So what we need to do is convert our T equivalent, right? So remember, this is Y, R, and X, right? We have to convert those parameters to this, and that's why we use Z prime and Y prime over 2. And we basically, in the T equivalent, the difference between the pi and the T is that we're distributing the capacitance on both ends of the line so that we can get the full effect of, okay, what if the sending end is happening, if power is flowing from Orrington to CMP, right? The receiving end is CMP in Cooper's Mill, right? But power is bidirectional, so what if the power is actually flowing in the opposite direction from Cooper's Mill to Orrington? Now the receiving end is Orrington. So if we don't want to get wonky results in terms of what's happening with our voltage, it's better to distribute that capacitance to ground on both sides of the line. And so that's why the pi equivalent really came out. So let's do a little circuit analysis. Yes, sir?
What physical thing is like the distributing the capacitance to ground?
So in the transmission line, right? In a real world transmission line, what is a real world transmission line? It is 3 wires, right? We have some capacitance between the wires. And if I'm looking overhead, right, we have some capacitance to ground, right? I have a piece of aluminum or an aluminum alloy, so it's going to have some resistance in all of them. And when I run current through here, don't I have magnetic fields that are there? these magnetic fields interact with each other, and that's where the inductance is. So the capacitor, the resistance, and the inductance are just from the construction of the line. And this is distributed over the entire length of the line, right? This capacitance lives everywhere along the line. So the idea is that I don't want to put the capacitance all at the beginning of the line, because it lives everywhere in the line, right? So I'll put some at the beginning and some at the end, and that, as long as that capacitance is modeled with those two capacitors, then I'm basically counting the effect of, all right, well, I've got one half on one end and one half on the other in case power flow changes direction.
So those are just big capacitor banks on each end of the line?
They're not real capacitor banks. They're the lines themselves look like capacitors. They're current. They can store charge, that it's a different potential between the lines or ground, and there's an insulator between them. That's the definition of a capacitor.
So is there a difference between caps between the lines and the caps to the ground?
It's usually going to be modeling the capacitances between the line. Capacitance to ground usually affects the zero sequence capacitance. Okay? But you still have, that still does impact, it still does impact the overall capacitance because you have something called line charging. So if you just energize a line and you don't actually run any current through it, you're still going to get some capacitance there because the voltage is there. Okay? All right, so let's do circuit analysis. So Vs minus Vr, what does that equal to?
Voltage drop across C.
Yeah, it's Vs minus Vr. And if I divide that by Z, what do I get? The current through there. What is Vr times Y prime over 2 equal to?
The current through,
It's that current, right? Remember, Y over 2 is an admittance. It's not an impedance. So I don't divide by Y prime over 2. I multiply by Y prime over 2. So the current into the node equals the current out of the node. This is just KCL, right? And since what I'm trying to do is write an equation for Vs equals A times Vr plus B times IR, right, which is our two-port parameters, if I reconfigure this equation and do factoring, Vs equals A times Vr plus B times IR. I have A and B through KCL. See that? If I do nodal analysis here, right, this current should be equal to this current. Now this is where I get a little fancy, right? This current right here is the same as this current right here, right? So all I'm doing is I'm skipping over and saying, all right, well, instead of doing this current, I'm going to do this current, which is the Vr times Y prime over 2, plus the IR there as well. All right? I'm doing that so I can introduce IR, essentially. I have to have an IR in that equation. So if I just did Vs minus Vr divided by Z, I wouldn't have introduced an IR equation in there, would I? So that doesn't set it up. So again, Is equals C times Vr plus D times IR. Is equals B times Vr. I'm sorry, not B, C. C times Vr plus D times IR. So I have a bunch of prime terms, Z prime, Y prime, because these Z prime, Y primes here, this one and this one, are not the original T equivalents. Those have to be adjusted. Okay? I'm pausing to make sure people see what I'm doing there. I'm just writing it in terms of ABCD with a new pi equivalent. That's all I've done. I haven't written it in terms of the original equations yet. I've just done it in terms of how to solve for ABCD. This matrix here is super duper important for you to understand. Nick,
Oh, actually, never mind. I see the matrix.
pardon?
The matrix answered my question.
Okay. It'll never change. It's always going to be this base form for the pi equivalent. And if you were to run Aspen one-liner or does PSSE, Susan, do you know if the PSSE does pi equivalents for their transmission line?
I have no idea.
Okay. I can show you in one-liner. I just can't show you on the iPad because it's not easy to log in. Yes, sir.
Kind of confused on how you got IS based off of. So you're adding, obviously, like sending. Times
Nope.
5 prime over 2.
Nope. So let me just erase this, and let's show you how I did that. Okay. So I'm going to do KCL for this node right here. Okay. Just going to do KCL. So I have this current here is going to be equal to this current
Okay, yeah, sorry.
plus that current, right?
Right.
But the thing is, my equation for my ABCD, you notice I have to multiply it by IR. I don't have an IR in here, do I? So what I do is I go to this next node because I know that this current here has to be the same as those two currents, right? So I've essentially cheated a little bit and brought in the nodal from that. So now I have this current is going to be equal to this current plus this current.
Yeah, I was just confused on the IR. 'Cause
Yep.
I thought, like, since we already solved for it already, but you had to also
You didn't solve for IR. Where did I solve for IR? Here? I didn't solve for IR. I wrote a nodal equation. I'm actually needing to solve for VS and IS, right? Because VR and IR are going to be known. Those are the receiving end quantities. I'm solving for VS and IS. Okay? That color coding make it helpful to see or not helpful?
Did I hear you say, which I don't think I did, but IR is the same as Y prime over 2? Like the current
No.
there is the same as the current there? Okay, good.
Nope. IR is going to be whatever the load current is. That's going to be something that you have to figure out, right? If you want to solve for the sending end quantities, you'd better know what the receiving end quantities are.
But you're not saying those two currents have to be equal?
No, they do not. Nope, absolutely do not need to be the same. This is just another way to do it. So 210, folks, you like doing two-port stuff? Is that what you were taught? Two-port parameters? No? Okay. Well, two-port parameters is you take a box, and whatever's inside of the box, right, should be the same. Yes, sir? Not exactly. Because it could be a mix. Usually with two-port, you can have all Z's, all admittances, or a hybrid of the two. So sometimes it's called a hybrid two-port parameter. So usually a Norton would be a current and a resistance or an impedance. This is usually not a current. It's just an impedance and an admittance, or it could even be a unitless quantity. So over here, right, if I look at my transmission line, and my equation, VS equals AVR plus BIR, what would be the easiest way to solve for A in that equation? Is it hard to read the green? Would you like me to switch to red?
Multiply by
Subtract. What if I made this go to 0? Wouldn't that be really easy? So A would be equal to VS B times R. The entire quantity goes to 0. When IR equals 0. Of course I can. This is a linear system, isn't it? A linear system means no matter what value I plug in there, including 0, that A term should work, shouldn't it? So A is going to be equal to VS over VR when IR equals 0. When will IR equal 0? When there's no receiving current, which means there's an open circuit. So this is Y over 2, Z, and Y over 2. I forgot the primes. This is plus minus VS. This is plus minus VR. Is there an equation that you can write very efficiently to solve for VR as a function of VS? Voltage divider. Whoa. It's like you read my mind. voltage divider, right? Because this voltage here is Vs, isn't it? Right? So doesn't VR equal 2 over y prime all over z prime plus 2 over y prime times Vs? Yes, no? Maybe? Uh-oh, I lost people. How did I lose you?
2 over y prime.
What are the units over here? Ohms, right? What is the unit of y?
Oh, 1, okay. Wow.
It's mhos, isn't it? So don't I have to invert it to get to ohms? Anybody want to do this math to see if you get here to here, which is exactly what we solved for in the first part, right? A is equal to 1 plus z prime y prime over 2. Isn't that what we have right here?
Yeah, the first one's easy.
You can do whatever you want. Either one is the same result. Okay? So now we have our ABCD parameters, right? How to go from the T equivalent to the pi equivalent. Now all we need to do is solve for our z primes and our y primes based on those original T equivalent. So we know in the T equivalent, that is our equation, right, for B? B is equal to ZC sine gamma L, right? From the original parameters. So that's just equal to Z prime. So you know what Z prime is. It's Z, characteristic impedance, times hyperbolic sine gamma L. That's how we solve for Z prime. Once we have Z prime, it's not the easiest, but it's easy to solve for Y prime. We're just going to use the A. So the A in the T parameters, our equivalent circuit, is cosh gamma L. Set that equal to Z, 1 plus Z prime Y prime over 2. And we're going to solve for Y prime over 2 to get that value. That's how we go from pi equivalent, T equivalent to pi equivalent. Okay? Make sense? So all we're doing is going from oops, sorry, I'm going back a little bit. Let me see if I can zoom in and do it faster this way. I'm going from here. That is the T equivalent network, right? That's where we started all our work. We're going from here, and you notice it's got Y. So this is Y. The combination of this is little z, right? And that's per unit length. But if we want to get it for the entire transmission line, we can make that big Y as long as we multiply little y times L and do the same thing to get big Z. We just multiply by the length of the line. So we're going from our T equivalent to our pi equivalent. And the process of doing that is here. So at this point, we know what A, B, C, and D are, all written in terms of hyperbolic sines and cosines and all that stuff. Questions? Because that is the exact way that you would solve for the transmission line equivalent circuit. All those hyperbolic sines, cosines, yada, 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 that's actually what you'll be doing. Okay? If you do that, you can solve for any sending in voltage and current based on receiving in quantities. And that's actually how you'll model transmission lines, is this pi equivalent using A, B, C, and D. Not these specific ones perhaps, but modeling them with these parameters. Okay? let's do a little bit of math to solve for z prime and y prime, right? So z prime is going to be equal to this, whoops, just the original z, right, which is the length of line times the actual individual impedances. And then our y over 2 is going to be this quantity here, okay? So it doesn't, hopefully it will be a little more simplistic. Now, it's still not great, right? That's a bunch of work. So what if we took a look at some of the line lengths? If we won 50 miles and we calculate sine gamma L, hyperbolic sine gamma L, gamma times L over gamma L, and do the same thing for the tangent, at about 50 miles we end up with that. Isn't that pretty darn close to 1 at an angle of 0? As well as that? Huh. So if I go up over here, if the line length is less, 50 miles or less, this right here equals 1, doesn't it? And that equals 1. So we can use the pi equivalent circuit if the line lengths are small. We can just say that z prime equals z. We don't have to do hyperbolic signs. We can do the same thing for y over 2. We don't have to use hyperbolic signs. We'll just say it's equal to y over 2. And guess what? That also applies for 100 miles. Pretty darn close to 1 at an angle of 0. Once we get to longer lengths, now we're getting to be 3% off. So you cannot use the approximation that z is equal to z prime and y is equal to y prime. You have to use the hyperbolic values. So this just tells you if it's a short line or medium, you can use this. If it's a long line, you have to use that. The shorter the line, the less work you need to do. Okay? Questions on that? Gamma is is it square root of L times C, or is it? I think it's square root L times C. It's in the notes. I just can't remember if it's square root of L over C or. Let's go to the beginning. It's all the way at the beginning. What is it? Let's see where gamma is then. I defined it up here. Square root of y times z. Not LC, YZ. Yep. So we'll summarize. If you're longer than 200 miles, you got to use the hyperbolic sines and tangents, which is not a huge deal. You just have to keep track of those. Make sure you solve for gamma, and then do hyperbolic sines and cosines, and you're good to go. If you have a medium line, 50 to 200 miles, you'll just use the z and the y. You won't have to use the hyperbolics. If it's less than 50 miles, that y value that you have here, this y over 2, is going to be such a small number, we'll set it equal to 0. So essentially what that means is in a small line, there's just not enough capacitance, right? You just don't have enough conductor to store sufficient charge to make a big enough deal. So for short lines, you can neglect the conductance. This is for overhead transmission lines. If it's underground transmission lines, you can't do that because the insulation is so small, right? It's a different characteristic. But for overhead lines, you can do that. Okay? So to summarize, for long lines, do I have it on here? I can't remember. Let me look. No, I don't. So for long lines, your A and your B and your C and your D, you have to use y plus y prime z prime over 2, z prime, I think it's y prime times 1 plus z prime y prime over 4, and this is equal to a. You have to use those values. These are your equations. If it's a short line, right, you're going to say y prime equals 0. Okay? So that basically will just eliminate any time that you see a y value, you just multiply it by 0. So for a short line, a equals 1, b equals z prime, c equals 1, and d equals 1. Which makes sense, right? Because in a short line, all you have is something that looks like this, right? So plus minus vs, this is is, this is plus minus vr. If I write vs is, what does ir equal? It equals is, doesn't it? So I would put a 1 in here, right? So is equals ir, and you have a 0 here. That doesn't matter what vr is. It doesn't change anything. What does vs equal? Well, it's equal to VR, whatever the voltage is at the receiving end, plus Z times IR, right? If I just did circuit analysis. A equals 1. B equals Z. Whoops, I should have put 0 here. Sorry about that. Because I multiplied the whole thing. C equals 0, and D equals 1. Exactly what we expect. Right, just looking at this base circuit. If it's a medium line, then I'm going to have y prime equals y over 2. So then my A just becomes 1 plus y z over 2. B is equal to z. C is equal to y times 1 plus y z over 4. And D is going to be equal to A, right? I can't cancel any of those terms out because my y term does not equal 0. If it's a long line, I'm going to have to do all the primes here. Okay? So y prime equals, let me use this color here, y prime equals this. So I'm going to just substitute in there because there's no way I can write that down. Z prime equals that. And then you got to substitute in all your equations for A, B, C, D. Okay? Make sense? Don't make sense? Want to see an example? We did a lot of talking, but to get to this point, now we're actually able to do an example. So here is a 345 kV, 3-phase, 130 kilometer T-line. So immediately, that should tell you the length of the line, right? Is it short, medium, or long? Short, medium, long. I got all three. Good guesses. 130 kilometers, right? How do you convert that to miles? It's about 5/8 of a mile, right? Give or take? No? Kilometers. To go from miles to kilometers, it's about 0.6 miles is a kilometer. So I say 5/8-ish. So if I do the math here, let's see, that's 650 divided by 80. So that's what, 81.2? So is that a short, medium, or long line? It's a medium length line. So what we can do is we can use these parameters here. So let's do that. First thing we're going to do is we're going to figure out what R, XL, and XC need to be, right? Considering it's a 60 hertz system. So we're going to multiply our units here, our ohms per, or our values per kilometer, and multiply it by the number of kilometers. Then we're going to multiply by omega, right, to get the x sub c and the x sub l. So we got an x sub l and an x sub c here. Now I'm going to build my y, which is r plus j xl. And my y prime over 2, or y over 2, is just going to invert this value here and divide it by 2, which gives me 0.274 micromos for the entire length of the line. So my circuit, if you will, becomes, this is J.274 milli, J.274 milli. I don't know why I'm scrunching up. I can do this. Sorry about that. This right here is, what did I say? 4.6 plus J, 39.21. And this is plus minus VR, IR, plus minus VS, IS. Now I can run that through my ABCD parameters. So I'm going to solve for ABCD. And I'm going to plug those into my calculator. And then I'm going to solve for my VS, IS, whoops. By using that ABCD matrix. Do I know what VR is? Sure do, right? 325 kV. Do I know what IR is? Not exactly, but I know what the load is, right? So I can calculate what IR is based on this power triangle. So if you build your power triangle, 270 MVA, if you zoom in a little bit, you see this 270 MVA. This is the cosine of that, or inverse cosine of that power factor. I solved for P and Q. I don't need to, but I did. Now I can solve for IR. I stick it in, and then this becomes my VR and my IR. Again, this is a V phase. If I want to compare the 325 to that number, I need to multiply this by the square root of 3. Okay? And then I like to draw the phasor diagram a lot, because what that tells me, if you notice the magnitude here of VS is greater than the magnitude of VR, that means that reactive power is flowing from the sending end to the receiving end. It also tells me that I have a phase shift between those two, which tells me that VS is sending real power to VR. So just by looking at this phasor diagram, I can tell you the magnitude of VS is greater than the magnitude of VR. That means QS is going to support QR. Because the angle of VS is greater than the angle of VR, that means power, real power, is going from the sending end to the receiving end. So all those operators that are working in Holyoke, Massachusetts, telling you, hey, there's this power, there's that, this is flowing, they can just look at a diagram and they can tell you the power flows just by looking at voltages. They don't even have to look at the actual flows. They can tell you just by looking at that. And then the last thing I did was calculate the power triangle at the receiving end. I'm sorry, at the sending end. Which hopefully will tell you, right? I'm putting more power into the system. And I'm also, because I've got some reactive power that's being consumed by the line, and I have that. So this would tell me that P, that 270 MVA, is greater than the surge impedance loading for this particular line, right? Because I'm consuming bars in the line, so that means the power demanded is greater than what the surge impedance loading is. You want to do that for homework? Check to see if that's the case? Who says yes?
We have a test tomorrow.
Yeah, but not Thursday.
Hey Paul, question.
Yes.
You have S equals VI conjugate and multiply 199.19 by 3.
Yep.
Up there you multiply by the square root of 3.
Yes. Is that a question?
Yeah.
Why did I multiply by the square root of 3 where? Here?
Down. In the matrix at the very end,
If we wanted the phase.
you have it.
Oh, because remember, if it's a phasor, you multiply by the square root of 3. If it's a non-phasor, everything else is multiplied by 3, right? So isn't this a phasor? That voltage is a phasor. So I multiply by square root of 3. The power here, this is a single phase quantity, right? This is a line, this is a phase voltage here. So I need to multiply it by 3 to get those. So that's with the 3-phase stuff. So who wants to do that as a homework? Does anybody want to check what the SIL is? It's a pretty easy calculation. It's just V squared over X sub C, Z sub C. And you know how to calculate Z sub C, right? Briar, you just told me what the equation was?
Did I?
How about extra credit? I think it'll only take you 5 or 10 minutes. All right. Have a great day. See you tomorrow at the test.